Okay, so let's get started. So welcome to the October meeting. Okay, so it's a intense meeting of this year now. So I still remember the first one. Yeah, so there are two topics today. One is we have, as you might have noticed, we have just released WasmEdge 0.11.1. So we're going to talk about this release. What are the new features, and why you should upgrade, right? And how can you contribute to development? Because I think there are important changes to the development process, or the way that we add plugins and things like that. So I'll ask Hydai to cover that. And after that, for the second half of the talk, we're going to talk about asynchronous applications in WasmEdge. What I'm going to do is that I'm going to demonstrate, a networking application and then a database application, so that you can see, how those two combine together to build a traditional microservice, that has HTTP server and also MySQL database on the backend. And I can also tell you about how we did that, and the crates we have published. I think there's 6, 7 of them. That's so it's a long tool chain that we have published last week to support all this. And then we're going to have some QA time, to discuss the projects you guys have been working on. Anyway, so Hydai, do you want to start with a new version of the WasmEdge?
Oh, sure. So let me. So can you guys see my screen now?
Yes, I can.
Okay, let's start. So today I'm doing the 11.1 review, and actually you can find that we just accelerate the release process, because in recent months, actually every month we have some very important features to release. So in this month, the 11.1, actually we are very happy to have the PyTorch backend support in our WasI neural network plugin. So this is based on the Ubuntu 20.04. Because some of the dependency will be a little bit hard to install on the for example, on the CentOS 7, the legacy system. So currently our WasI neural network will based on the Ubuntu first, then and we will do the some more porting stuff to man this can run on the managed system. Okay, so you can get this example from our WasmEdge book, and if you want to build this plugin by yourself, then you can. So if you want to build this plugin on your platform, please use the this option, which is the the WasmEdge plugin WasNN backend, and just specify the PyTorch. Because of our our current setting, so you will need to specify. If you want to use the OpenVinyl, then just change this to OpenVinyl. If you want to use the PyTorch, please just specify it. And the other thing is that we are very happy that the OpenSSL is released the 3.0 version, or 3.x series, and because our previous the WasI crypto proposal is based on the OpenSSL 1.1.1, and we just made some changes to fit the new version. So this two is is the major features in this release, and we found that the LLVM 15 is just released, and if you are using the Mac OS, you can find that when you use the brew install, you will get the latest LLVM, then you will cause some some built-in issues. So we just fix it. And we also provide a new, the new plugin framework in C style. Our previous plugin, such as the WAS neural network and the WAS crypto, we are using the C++ version. And after this release, we have the C version 1. However, the documentation is still underway, and I think you should, we will just add some documentation in next few weeks. Yeah. So if you are interested to use this, and you can, just raise an issue or something, and we can help with that. Also, we add two improvement in our CLI tools. The first one is that because on some platform, especially the Mac OS 1, if you want to use the universal WASM format, you may encounter that if you use the default setting just for the optimization level 2, then the universal WASM will fail to execute. However, we add this option, so you can set the optimization level to 0 or 1 or 2, just to avoid that situation in some specific platform. And also, if you want to print or return the 128 length integer, then now it's fine to print. Before this version, well, you will just print nothing, and you will get the program is success asset. However, you get no result. However, with this support, then the value can be printed now. And also, because that our WAS neural network plugin is based on the Ubuntu 20.04, so we have also released a version on the Ubuntu 20.04. However, if you want to use this version, you may need to just download it from our release page, because our installer will use the many Linux version by default. Okay, so just a lot of environment issue, and we will continue to improve it. So we also have 2 bug fixes. This is the most important one. So the first one is that this is an internal one. If you are you are just develop some bindings or develop some plugins with our our internal module instance, then some of the member actually is not exposed with the right permission, so there will be an issue. Then it's fixed. Another thing is that actually we have a type of mismatch of the interest table. So if you use our ALT compiler to compile your WASM application into LLVM IR, and when you get the IR, if you try to use the LLC to compile it, then you will receive an error just for the the type of mismatch problem. So we also fix that. Okay. So I think this is the last part, that we just enable the initial fuzzing test on our WasmEdge CLI. So in the next few months, I think we will have lots of issue according to the fuzzing result. And also the WasmEdge book is just do some reorg. So if you if you are using the WasmEdge book, you can find the organization may change. So if you encounter any issue, for example, you can find the page or you can find some content on the website, please, open an issue to tell us. We will, just fix this as soon as possible. So in the end, I want to give a special thanks to all those contributors. With them, so we can have this version. Thank you.
All right, thank you, Hydai. Yeah, that's I encourage everyone to try it. Just it is actually very easy. It's I think everybody on this call probably already had WasmEdge installed, so you can just run the installer command again. That's it would automatically upgrade you to the latest version. I would also there's two I would also encourage everyone to try out those plugins, especially with the AI ones like PyTorch and OpenWine. PyTorch is, I think, especially interesting because it has just joined the Linux Foundation, right? It has become a community project now. I think it's our challenge with TensorFlow has always been, we don't get a lot of support from that community because there's, I think, less people using TensorFlow. Much, that's it's unfortunately Google is not putting a lot of effort in it. So you can see that even Google, they use JX now, JAX now. So but I think PyTorch is entirely different. There's lots of people, especially open source guys and people in university and things like that. There are lots of models you can try out. So we really look forward to see what you guys can do with those. But let's move on to the second topic, which is I want to show you how to create asynchronous applications in WasmEdge. And let me share my screen. All right, so everybody can see that, right? Okay, so the first demo I want to show you, it's here. You can follow along in your own browser. It's under the WasmEdge organization, is a project called a Hyper demo. So for those of you who don't know that, Hyper is one of the most popular HTTP framework in Rust. So if you want to write a Rust client or Rust server, you use Hyper. And one of the chief benefits of that is that it provides asynchronous. It's when you say asynchronous I/O, it means non-blocking I/O, meaning that's in a single thread. You can start listen to you can make a request or listen for incoming request, and when you do receive a request or a response, you can move on to do something else. Let me see. There's a chat message. Oh, okay, yeah. So So thank you, Vivian. So the link to this repository is posted in the chat. So once you have that, once you receive a message or receive data from a connection, you can wait, for data to come in while open another connection to handle something else. That allows you, even in a single-threaded environment, to do multiple concurrent connections because, as we all know, computing is fast, but networking is slow, right? So you can wait for those data to fill up, so to speak, and then, do, perform the computation, that may or may not be related to the data, right? So, that's a chief advantage of, what we call a single thread but multitask, right? So that's actually exactly how Node.js does servers, because JavaScript is a single-threaded environment as well. So, if you come to this repository, you can see there's a README that tells you, oh, actually I need to change this README. But I'll do that in a minute, but we can look at the code. So there's 3 projects. There's a client, there's a server with TensorFlow Lite. Okay, so the client is pretty straightforward. So let's go ahead and look at the server. Yeah, and look at the see that. So it's really pretty easy. Just build it with the regular cargo command and use WasmEdge to run it. It would start the server and listen to the port number that you specified in the Rust code, and then from another terminal you can curl it, right? You can send something to it and it would echo right back. And let's look at the implementation. So it's a single file. It's called main.rs, and that's all there to it. It's pretty straightforward. So the server is an asynchronous main function. So the main function opens a socket address, at the local machine, 8080, port number 8080, and start listening to it. Okay, and they start a loop. Whenever there's new message, when there's a new connection comes in, so this await message returns. Okay, it's accept, it's keep waiting, and it's when there a new connection comes in, it returns. What it does is to spawn a new, not a new thread, but a new task in the same thread. That's to say, I'm going to use echo to process this message, and then it goes back to this loop. Okay, because this await, that's so basically it's a process. Whenever it's a loop. Whenever a new message comes in, it spun out a new it spun out a new task to handle this message, right? So even like I said, because all those are non-blocking, so you can have multiple concurrent connections at the same time. So in a task response, it uses the echo method to, because it's specified here, service function is echo. So it uses the echo function to process the message. So the echo function takes the HTTP request and respond with the HTTP response, right? So those are all, functionalities provided by the Hyper framework, right? So in the echo method, you can take the request and see, and match its HTTP method. Is that get or post, and the path, what's the URL that in the HTTP request. So here you can say if the user just gets the root directory, just to say localhost column 8080/, it would return a message that says, please use the echo endpoint. That's you can't use the root endpoint. If they do the echo endpoint, however, it would just be, the response would just be the request, right? So we take the body of the request and send it back into the response. So that's really, this entire thing. That's that's the entire server, really. That's all the logic. That's the server. Everything else is boilerplate, right? And then we have a little another function which is really not, we just for demonstration purposes, we don't actually use it, is to say echo reversed, right? So if you hit this URL, it would take the content from the request, reverse it, and then send it back, right? And everything else you would say we would return 404. So that's, you can see that's a pretty straightforward, server, right? That's it's 50 lines of code, and it uses the Hyper library from Rust, and you can see, it's important things like the Hyper service function. Here is how it specifies the echo function. Use the echo function to handle HTTP request. It has things like, those HTTP elements, right? When HTTP request comes in, to know how to pass it. That's also in Hyper. And then in Tokio, Hyper depends on Tokio. In Tokio, you have the TCP listener, where you open the socket connection and listen to the incoming connection. So those are all very standard Rust APIs, right? If you are into Rust programming, you even if you are not into Rust programming, you should that's this 50 lines of code should be pretty straightforward. That's you open up a socket connection, you loop around it. Whenever a new connection comes in, you open a new task. So you have multiple tasks running at the same time, and then each task has a service function where it knows how to handle the request, right? That's it. So how do you build and run this application, this very small application, what we call microservice, right? It's because it's HTTP service that you can run. Is you can go into the GitHub Actions commands. So here is the server example. Most of it is really just to generate a nice output. So you go into this directory that I just showed you, this server directory, and then you issue a command that is just regular cargo. There's nothing fancy about it. Just build it to the WebAssembly target. And this step is optional. The WasmEdge compiler is optional. It's what it does. It does the AOT compilation of the WASM file that's generated from cargo, right? So it's cargo would generate from target release and a WASM file that contains the WebAssembly bytecode. But on this, but on the machine, on the the server in this case is GitHub's Azure machine. That you want to you could AOT compile it into another WASM file that has the native instructions, which would speed up. In many cases, it would speed up computation by, I think, oftentimes 100 times. So once you have the application compiled, you can now run it, right? So the key command to run it really is this. So use WasmEdge to run this WASM file, but we put it into the background so that because it's a server, right? So that we can interact with it in the same terminal. Okay, so we put it into the background and we capture the process ID that's from the background process, and we sleep for 15 seconds. That's just give it abundant amount of time to set up. It's typically done within a couple of milliseconds. So we don't really need to sleep here, but but there's a little bit of delay. If we just immediately issue another command, it would be the workflow runner going to run the next command within 1 or 2 milliseconds. So it may have problems. So we sleep a little here. That's essentially any amount of time is good. So then we can do the curl command. So because it's running in the background, so we request localhost 8080 is the port that we listen to, right? And the /echo is, if you remember, that's the URL endpoint that we specified, right? That's if a post to echo that we return, we echo back the body of the request, right? So, and then the body of the request is WasmEdge. And the result from the curl is captured in the variable called RESP. And after it it gets this result, it echoes this out, and then it kills the process. And then it determines if the response contains the word WasmEdge. If it is, then this CI task passed. If not, then we failed, right? So let's see how it's running. So when you have it, in the GitHub CI, you first set up the environment, you install install WasmEdge. Let me show you how we installed it. So you can see we installed the latest version, 0.11.1. And we installed everything here. And so you can see the install log. And there's a client example I want to show you. And then here's the server example. Server example, if you recall the first process, the first step is CD server, enter the server, and then run the cargo command. The cargo command would build it. So because Tokio and Hyper has a lot of dependencies, so you can see it takes some time to build it. And then this compile start, verify start, and things like that's WasmEdge C. It does the AOT compilation. Now it runs it. It's print out to the console to say listening on this, because I have this line of code here. It says print listening on HTTP this, right? So it shows here. Come on. And then what's you don't see here is that we do a curl, right? That's once we do a curl, it's we set up curl in the way that it's going to print out the progress in the console. So it shows you, it makes a connection and to the server, to the hyper server we just built. We just started and then received some data back, and the data printed to the console is WasmEdge, right? Then it's then we kill the process, and then because the response contains WasmEdge, so we say execution is success. So that's the whole server. That's it's really, here's a command. I just talk about, right? So actually, in the next example, we can just show you that. So this is really quite straightforward. That's there's nothing fancy about it. So what I can do is I'm gonna close this tab. Yeah. So then let's see another example. Because we see there's two server examples. Let's see the TF Lite. What this does is to do TensorFlow inference or the or the AI work. Although I really would like to have a PyTorch example. So if you guys want to contribute, that would be a great opportunity. Because now we have 0.11.1. That's get a fancy PyTorch model and then write a hyper server for it. That's I think that would make a super impressive demo. So we can see the so this example is a little more complicated, and you have models here. That's essentially you have the MobileNet model and the food model. I think we are using the MobileNet model. The food model is just a MobileNet model that's specially trained for food items, so it would be able to recognize food. So this is the TensorFlow Lite model that's trained, and then here is a label file, meaning that's when you run this model, you're gonna get a we're gonna see in a minute, you're gonna get an array back. The array would be a bunch of numbers, and the first number in the array corresponds to the line number in this. So if the first number is 60, it was telling you what's the probability of having a water snake on the picture you have just set, right? So those are quite straightforward. So now let's look at the actual application code. So the actual application code is, for the server, it's identical. So you have an asynchronous main function that starts listening at the socket, and when there's a request coming in the socket, you start a new task and specify the service function called classify. Okay, and then you go back to listen, because classify is an asynchronous task. It knows how to. It may take a long time. It may take. I think in our case, it may take a couple milliseconds to to run the entire AI model to get a result, right? And in this time, it can go back to the it can accept another connection and run another instance of the classify model. So this classify function is shown here. I think I've shown a very similar thing last week. So it's an asynchronous function that takes the request and returns the response, right? What it does is that it's by the way, all this, the interesting about this is this looks like runtime thing, but it's not. It's actually happened on the compile time. Those include bytes is a compile time macro. So it's at a compile time, it's already took the TF Lite and put it here. So so at runtime you don't need to read the file system at all here. So that's all the data is actually in the bundled in the application already. So you have the data, you have the label, and if you go directly, if you get the root, it's going to tell you you're not supposed to do that. What it wants to do is to post to classify. What do you post to classify? Is to post the picture that you want to classify, right? You send a picture and ask the computer to tell you what it is, right? So what it does is that it extracts the body from the picture and then construct the image, a JPEG image from that body, and then it runs through the AI, the TensorFlow API, which is PyTorch is very similar. What it does is that it takes a picture and turns it into a tensor, and then use TensorFlow to run the model against the tensor. And once you get the result, this is a result vector. You can analyze what's in the result vector. It's all dependent on the model. So in this particular case, we have the line number that corresponding to the label I just showed you, the water snake, remember, right? And then the second one is the probability. It's a number from 0 to 255. And if it's 255, it means there's 100% probability of this object happening. That's on the picture. But most of the time it's between 0 and 255, right? So in here you iterate through the return matrix and to find out what's the highest probability, and then find it and then match it to the file, to the label file, and then print it out. That's as your return result, HTTP response, to send it back to the user, right? So as you can see, this process, could, although it runs really fast on WasmEdge, but for a complex AI model, it could take some time. And what I want to emphasize again and again is that during the time it's spent processing this model, it can actually, you can have another connection open and receiving data at the same time while you're processing this. Okay, so you have multiple connection going on at the same time, and it's done in a way that is asynchronous, right? So now you see all the code, and let's see how it's run. And so let's see the commands we use to run it, and go into this directory first. And this is exactly the same. It's use a regular cargo command to build it into the WASM bytecode, and then use WasmEdge C to do the AOT compilation. So basically you turn a WASM file into another WASM file. This is not entirely necessary, but it will speed things up. And then you run this. For TensorFlow, we still have a separate utility command to run the TensorFlow version of WasmEdge. But what I have been super interested is PyTorch and OpenWino, because they are developed as proper plugins, which TensorFlow we're going to convert that to plugins as well. So with PyTorch, you're going to just use WasmEdge. You don't need WasmEdge TensorFlow Lite, and run this server. The server we have just compiled, and do this, and then when you run curl, is that you give it the URL, that's port 8080, the path is classified, and then you post a binary data from an image. Okay, so basically you put the JPEG image and put it into the HTTP post body, and send the whole binary into the endpoint. Post the whole binary into the endpoint, right? That's if you remember on this side, we take the request and extract all the bytes from the body. So essentially, we can reconstruct this JPEG image on the server, and then we can run the AI model to detect what it is, right? Now you can say, that's then you capture the response, and then test what's in the response, right? So we're gonna see what's in the response. So you compile this and do the AOT compilation, and then it starts. It ends with the server running. Server runs on here, And what is the picture we send it? Okay, so it's a very common. Okay. It's this picture. You guys know who she is, right? It's Grace Hopper. It's one of the most famous computer scientists, and but it would not recognize who she is. It would tell you what's in the picture. Okay, so what's the most important? The thing that strikes you in the picture as an object. It's a military uniform, right? That's the most important thing. That's the most visible part of the picture. So you use the curl to send the picture, and then curl responds the result back. And this is the result that printed. Its military uniform is detected with 206 over 255 confidence, meaning that's, it's fairly high confidence. That's like I said, it's 255 over 255. That's 100%. So the computer is absolutely certain that this is that, right? So you can have. So this is how you do AI inference. That's as you can see, using Hyper, it's easy. That's there's really nothing. You won't even feel this is using WebAssembly or a non-supported target. That's you just use the APIs that you're already familiar with, or you will learn in Rust to create a server and just use it here, right? So, but this is only half of the story, because if you want to write or run a microservice like that. Oh, by the way, since we have that, we really don't need Docker anymore. Not need Docker anymore, not need a container anymore. Actually, we got we are working with Docker to integrate WasmEdge into the Docker CLI. We will have a really good demo, and I think someone on this call, has integrated WasmEdge into Podman, which is Linux open source Red Hat version of Docker. So that's that would really allow us to use those tools to create microservices. Because today, what if we want to do a server that's written in Rust? You compile Rust to to the native code, right? And then you use Docker or Podman to start a Linux container for that. Now you don't need to do that. You just use Docker or Podman to start a WasmEdge instance, and it would have it would run a server that is much lighter. It's maybe, I think, 10% of size, or even 100% of this, and even 1% of the size. That's you'll be able to run a server like that, and then turn that, essentially turn that into a microservice, right? However, this is only part of the story, because a microservice is only useful when it has. There's many use cases for stateless services. For instance, this TensorFlow example is a good example of a stateless service, because you're sending a picture, and you may need to log it, but you really don't need to maintain any state from invocation to invocation. So it's so each request is independent, right? But in a lot of use cases, you do need state. You need a database that's backend, right? So you need something that's that you can save temporary data, so that you can say the user is logged in, his shopping cart, his whatever. That's so you need state for services in a lot of cases. Can we do that? And the answer is yes. There's here's the second project that I want to show you. It's called WasmEdge DB project. The DB examples, essentially it shows you how to access database, MySQL database, from the WasmEdge runtime. And what I want to show you is MySQL async, because this is the same as the HTTP server. If you want to do this kind of thing in a single-threaded environment, you really want async, so that when the data is coming in and out, the CPU or the processor can do other things. So it can at very minimal accept another request. right? So that you can have multiple things going on at the same time. Otherwise, those network connections would really block you and degrade the performance, because your application would run as fast as your network, essentially, right? So that's so what I want to show you here is a async MySQL example, and it use a popular MySQL driver in Rust. It's called MySQL async, right? So let's look at the code. So you import MySQL async. It's exactly the same way you're going to use the regular MySQL async library, and you define a function that give it the database string. That's although we're going to pass the database string in environmental variable, but if it doesn't, you have a default. And what's interesting really is that you have a struct that's called, here we call it order, but it could be anything. It's maps to a database table in MySQL. Okay, so in MySQL you have database schemas. Because the really nice thing about Rust is that it's a strongly typed language, so you can have the database schema in the database that is mapped. It's very much like the old days in Java. We do ORM, we do Hibernate, right? That's the same type of idea. You have a data structure in the programming language that maps to the database table. So you have the column names and the data type, things like that. So this is your data model, and once you have that, you can do the main function shows how it works, right? So the main function really is that you have a asynchronous main function that's running by Tokio, right? And you build the URL and build a connection. So this is a long way to do it, because as we talk about, there's it's asynchronous. You can have multiple concurrent connections, and so that's so here we can build a connection pool that we can have 5 or 10 connections that we can reuse. That's in a high-speed environment, right? But you don't have to do that. You can, if you don't need to mess with the connection pool, you can just use this piece of code that is easy, right? You just open a connection pool with the default values and get a connection from it. Now we can do the SQL commands. So here are the SQL commands to create a table if it doesn't exist and all that. And now we create a bunch of order objects. Okay, so create a vector for order objects, and then use this SQL command to say I want to insert all those objects into the orders table. So now we have an orders table in the backend in the MySQL database. We use iterate over the orders array, which is here. That's and it takes all the order structs in the array, and then generate a SQL command, which we would then send through the use the batch processing command and use the batch processing function that provided by the driver to the connection that we just pulled from the connection pool, and then wait for the result to come back, right? That's asynchronous. That runs asynchronously, and so that's the insert. And then you can do the select as well. Select everything from orders, and then with the result coming back, you put those results back into the order object. Okay, it's not an object; it's a struct. That's so you generate a bunch of structured data from it. So as you can see, this we have tests for all the SQL commands, these current commands. The create, read, update, delete, right? So we have all this, and so this is a complete example. Each it shows you ORM, how to map Rust data into SQL, how to get connections, how to issue those SQL commands, how to construct the data back to Rust object, and vice versa, right? So it has all this, and now let's. Yeah. Okay. So Vivian has a URL in it as well. So let's see the effect, how it's run. So this is a fairly complicated CI task. So what it does is that it installs and runs MySQL. Let's see. Yeah, so it's used the Linux, it's default MySQL package. It also installs and runs TiDB, just to give you another MySQL example. Okay, that's so TiDB is no longer Linux package, and you can see we installed it from its own website, right? And then start it to make sure it's running. So here it's waiting for TiDB to start, and I check the status every like two milliseconds or things like that. And here it's done. TiDB got started, and then we have another KV store that's called Anna, which we're going to talk about later. We won't talk about right here, and then we can say MySQL async examples. What it does is that it enters that directory I talked about, MySQL_async, and then use the cargo command to build it. Again, it's a very simple cargo command. That's there's nothing fancy here. Just very straightforward cargo build. And then again, WasmEdge C to compile the regular WASM file into an AOT WASM file. This is optional. And now we can say we use WasmEdge, but we pass the environmental variable to it. The environmental variable is, oh, this is nice. It hides the username and password, although the username and password are nothing. That's so the URL. So the database URL points to the local MySQL instance, okay, and points to the MySQL table. And then so this is the environmental variable, and where the program going to take it and use it to construct the connection pool, and then we pass the program to it, and then we get the result into the response, and then and then show you whether it's successful or not, and then you can see the log. What it does is builds. It's an even longer build because the MySQL driver has its own dependencies, so it takes almost 3 minutes to build it. And then it's it has a process to do the AOT. It compiles, it verifies and output, and then you run it. When you run it, it's connected to the MySQL database we just started from on the local machine, and then it creates the table, and then it creates the table, inserts the data, and reads the data back, right? So you can see the order objects here being printed from the raster debug command, and you can and then this is 5 records, and then you delete one. There's 4 records, and then you update one. So you can see all the SQL command done properly, right? So this is this is how you do a SQL database in WasmEdge, and so if you guys have time, that's another idea of contribution is really to write a microservice that has a database backend, because now I have shown you the 2 legs, right? The HTTP from and the MySQL from. It should be fairly easy to write a demo application that has both. That's take something from the HTTP request and save it into a database, right? Or take a command from the HTTP request and read something out from the database and show the result to the HTTP caller, right? So all those are now within reach, because those are, I think, perhaps 90% of the microservices out there are like that, right? It's just something that sits in front of the database. So that's that's the code I want to show you. But I also want to show you a little bit of how we did it, right? So if you look at let me think which one is best. Okay, this one. If you look at the cargo dependency file that we used to compile this, it's a very simple file. But instead of Tokio, we have something called Tokio WASI. Instead of MySQL async, we have something called MySQL async WASI. However, in the code, it's exactly you can just use Tokio. You don't have to use Tokio underscore WASI in the code. You just need to use it here in the cargo dependencies. The reason is that at this moment we have to fork Tokio in order to support this, because the WASI socket is not yet a standard. It has been like that for 2 years, right? That's so once that becomes a standard, we would I think we should be able to merge those changes into Tokio. But it's a long toolchain, and you can as you go through those examples, you can see that it started with MIO. That's a Tokio library for IO. It's called Metal IO, right? So we have the MIO underscore WASI. And then up on top of that, there's Tokio WASI. There's Tokio Utilities WASI. And on top of that, there's Hyper WASI and Request West WASI. And on another branch, we have MySQL WASI and MySQL Async WASI. So it's a chain of crates that we forked from the official projects in order to support this. We hope that we would be able to merge it back upstream once the WASI socket standard become more stable, or when there is a standard, right? But at this moment, I think this is the best user experience that we can provide. Is that in the cargo command, you use the WASI version of those popular crates, and then in the code you don't need to change anything, because that's we aliased or we mapped those package name to the regular Tokio name, to the regular package name that's without the WASI, right? As you can see from the code, there's no Tokio underscore WASI in the code. So that's what we did. Okay, and then there's one last thing I want to talk about, that is Anna. So here we have an example called the Anna DB. So Anna is one of the projects that we are involved in, and if you guys are interested, I would also encourage you guys to look into that. It's a very, very interesting project. I'm sure you guys have all used Redis, right? The in-memory database, the in-memory key value store that is super fast. However, Redis's problem is that it's single-threaded. So although it's very fast, but it's really difficult to scale, because it's even on the multi-core CPU, you have problems scaling Redis. So there's lots of work has to go into there. So Anna is a PhD project from UC Berkeley a couple years back. And so they published a series paper from it. The topic really is what they call coordination-free key value stores, meaning you can have a cluster of Anna instance or key value stores, but they don't need to coordinate with each other. They just need to send each other asynchronous messages, and the recipient can process the messages when it's free. Okay, so you don't need to interrupt the workflow to do synchronization and things like that. The result is that it's a key value store that's as fast as Redis in a single-threaded environment. However, it can scale up, to multi-core CPUs and to multiple nodes, which makes it super useful for edge computing. Because if you think about the service that the microservice structure that we have just talked about, you have a HTTP-based microservice with a database backend, and the best practice or the design pattern calls for one database per service, right? That's if you look at microservices book, it's number one thing they talk about, one database per service, right? So this database really should be something like Anna, is that I can interact very, very quickly with a microservice. However, I know, the database itself knows how to synchronize with the rest of the system, so that it can provide a consistent state across all the nodes. So what Anna does is that it provides, a different level of consistency. You can do transactions with it. which kind of slow it down, but you know, you can do it. But you can also do eventual consistency, which is the fastest mode, right? You know, so for a lot of data, which, you know, it's not transactional in nature, you know, it's not banking or blockchain data, but you know, it's, say, image recognition, you want to save the image. It's not essential for all the nodes to have the exact same thing at all times. You know, that's if they go out of sync for a couple of seconds or a couple of minutes, that's fine, right? You know, so Anna would be a perfect use case for that, because each application would have its own database, and all those databases are all connected somehow, you know, through the Anna's infrastructure, so that they can be eventually consistent, but they can be super scalable, right? You know, so that's why I want to make this demo, because I thought, you know, the MySQL example is great. However, you know, do we really use MySQL? You know, I talk with a lot of people in edge computing and all that. You know, that's actually one of the questions. You know, do we really need to use MySQL? You know, so it's you know, the NRDB, I would really encourage you guys to you know, to look into that. It's also written in Rust, and we made a lot of contributions to it. We built the drivers for it, right? You know, we are also committed. You know, so the plan really is to make it Redis compatible. You know, so basically provide a richer API to it, so that it can be, yeah, it can be, you know, compatible with the Redis client at the API level. That would make development work a lot easier. So, you know, we can just take the Redis driver and put it in WasmEdge, and we would have a, you know, we would really have a complete story here. So anyway, yeah, that's that's all I have, and it's end of the hour now. And yeah, so if you guys have questions, comments, or anything, you know, that's we're gonna hang around for another 5-10 minutes. You know, so if you have things you want to discuss, that's we can talk about here. Thank you.
Hi, Michael. So
Yes.
the Async capabilities are totally interesting. So in the past, we needed to have some host code and spawn an WasmEdge instance in a separate process to have parallel HTTP workers. And now we can do this all inside the Wasm VM, which is, I would say, makes WebAssembly containers even more interesting and usable. So very looks good, and I really like the database part. So yeah, thank you for that.
Yeah, thank you.
So
if
we would have 2 more minutes, I could share some very small insights about the state of containers. We are working at Liquid Replay at the moment. So
yeah, please, yeah.
Okay, I can try to share my screen. I need some more permissions to do that.
So Vivian, can you let me see if I can do it on my end. Yes, I can see. Okay. I think you should be able to do it. Yeah.
Okay. Let's share the screen. I hope you can see my screen.
Yes.
It started here with the announcement of your talk, so you may know that. So,
yes.
As I read it, it's a talk about how to use pure WebAssembly containers with Docker as OCI runtime. And I've already seen in our documentation there are some short, I would say, stubs. So the first one is how to use it with Slim containers, and the second one, how to use it with a containerd shim. But there is a sentence. However, we cannot easily replace OCI runtime, run C, in Docker toolchain with crun. And
that's correct.
Yeah, so the interesting thing for me, I have a problem with this taskbar from GoTo. Okay, so my idea was, why not use Podman, since Podman already uses crun, and the only thing on a Linux installation you have to do is to compile crun with WasmEdge and replace your existing crun, and then interestingly, you can just say, with annotation that you want to have a container exactly like you would do it in our Kubernetes examples, and it's basically working. What was totally amazing. And then the next thing is, what can we do for Mac OS and Windows users? And there, Podman is using Podman Machine. And for that, I have this repository where I just added the changed the C run in the image. So on an Intel CPU, you can use this URL, which leads to the releases page, and can use this images with your Podman installation to have Podman Machine and do it on your Windows and Mac machine. So what we found very important for the development flow is this missing piece between the WebAssembly VM you're using on your local environment and the Kubernetes environment. And the piece in the middle, what was still missing for many developers, is just using your container on your local machine with Docker and or Podman here. And I think that's a very important thing, whatever you are using. So be it Docker or be it Podman, it's definitely improving the development flow. And then due to some requests, how can I use it with my Kubernetes distribution XY? We started a very small project. So this is only the proof of concept with an alternative way to use it with kind. And you just apply a daemon set to your existing cluster, create a runtime class, and then you can just execute your payload with another runtime class.
Okay.
And it is then working. How that magic works, I would like to share in more detail, in the next community meeting, when this project is more polished, and then hopefully is running with all the managed clusters of the major cloud providers. So
yeah, that's
would be looking forward to that.
Yeah. That's we love it. You know, that's you know, one of the things. You know, I think it's a big missing piece because, you know, that's we are working with Docker, but mostly on the tooling side, you know, because Docker CLI has a very large user base, and we want, you know, developers to be able to, you know, start WasmEdge directly from Docker CLI as if it's a Linux container, right? You know, so that would make a lot of the thing we talk about. It's, you know, could be easier for developers because they don't need to install WasmEdge and, you know, things like that. They can use their existing you know, workflow. However, Docker CLI is not you know, commonly used in Kubernetes. But I think the is really interesting about Podman is that it's on the CLI side, I think it's a computation alternative with Docker, right? You know, but it's also, as we have demonstrated, it can easily be you know, integrated into the Kubernetes environment. So I think that is actually really good. You know, that's so let's work on this together. You know, that's you know, because you know, KubeCon is 3 weeks from now. You know, we're gonna be there. We're gonna have a booth. We're gonna have that. You know, if we have a demo on Podman, that's we're gonna have a big TV screen there. So our plan is to play all those demos on the TV screen. So, you know, so if we can have a demo that we can do with you, that we can have a little video that although there wouldn't be any sound because it's on the show floor, so it's going to be really noisy. But you know, we can have captions, right? You know, to say what we are doing at every step. You know, like the demo you have just shown, right? You know, that's here's how to do it on Podman. Here's how to do it with Podman in Kubernetes. You know, that's I think that'd be really really good. We can point people to it, and you know, that's you know, to get more people to be interested in and perhaps contribute. You know, I love it.
Yeah, sounds really good. So I would try to target the next KubeCon in Amsterdam, so KubeCon EU, and then it would be awesome to have an async HTTP example with database backend running on Kubernetes. So
yes, we can do it.
Would be my target for next KubeCon.
Yeah, we can do a Shopify. That's that's excellent. Thank you, Sven. Yeah.
Thank you.
Hey, Michael, it's Brad Jones here.
Hi, Brad. How are you? Yeah.
I'm good. How are you? Another fantastic meeting here. I'm sure I'm going to make you repeat yourself, but can you review a little bit about what may be the barrier or barriers to having WasmEdge run on iOS?
Oh, the
I'm
thing
sure you
about
could. Yeah.
Yeah, the thing about iOS really is that it's a closed system, right? The App Store, guidelines specifically said no virtual machines.
Okay.
That's
what I figured. Yeah.
Yeah.
I figured that. And so, but
I mean,
outside of the App
Android,
Store, is there any technical reason outside of the App Store? I mean,
no, I don't think it's I think it's an incentive problem because because it takes effort. We're already running on the Mac, so it shouldn't be that hard to run on iOS.
That's
However,
what I figured. Yeah.
Right. But who's gonna use it? If we run it on iOS, we're gonna, it's gonna be super difficult to demo, and also super difficult to explain to people. Although I actually think there's a lot of value because that's why we did Android version in Open Harmony, because because it provides a compatibility layer. It's like Amazon did with their media player. So they have a very good case study that says they have an Android device that they need to target like 200 different underlying devices, and they also need to run fast, so they need to use C++ or Rust, but they can't build a native application that runs on Android because there are too many variations of devices underneath it. So what they did is that they used a WASM in the middle, and I think they used the WAMR. That's the lightweight WASM runtime, and that's indirectly embedded that into the Android app, and so then on the development side, they just need to write this C++ code once, and all the clients they have embed a WASM runtime. So this is a model that's, I think, it's super useful, and with WasmEdge, you can because WasmEdge, in the grand scheme of things, it's thinks that the distribution is 4 megabytes, 5 megabytes, or even less than that. So you add this, but you can do things like you can access GPU, you can do AI inference, and things like that. Much more, you can do networking, you can do much more advanced stuff that's in your Android application by using WasmEdge as a compatibility layer. But that's at least that's my idea. That's I believe VMware has a project that's trying to do that. But iOS is hard. It's just we can't have we can't have anything that's not approved by Apple yet. Yeah.
Right. No, I figured that. Okay, that's great. Thanks very much.
All right. Thanks. Thank you. Yeah.